Okay. 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 Let's get started. So, welcome to week 6 of Computational Systems Biology. So, I am the PMRFTA. My name is Shomo, and this course is conducted by Professor Karthik Raman of IIT Madras. So, last week in week 5, we discussed about different types of differential equations and how you can construct those equations and models from chemical reactions and biological processes. So we saw how different reactions can be modeled using differential equations and how those can be solved as well. So today we are going to look into one special kind of computational algorithm which uses biological insights of evolution and mutations, and how we can how these genetic algorithms are constructed using the information of evolution and mutations, and how we can solve these using genetic algorithms. Yeah. Okay. So, what are getting started? What are evolutionary algorithms? So, basically, evolutionary computation is basically involving biological evolution, integrating the principle of biological evolution into algorithms for solving complex optimization and design problems. That is the whole idea of evolutionary computation or evolutionary algorithms. So, one case of evolutionary algorithm or computation is genetic algorithm, which we'll come to later. But generally, this is the idea. So what all things can you optimize? So for example, you can make an optimization, you can form an optimization model and make it and get an equation for, say for example, internal combustion engines, and you want to optimize it for fuel efficiency, or you want to optimize graph theories analysis using this evolutionary computations to find fully connected subgraphs inside a bigger graph. You can use to solve biological problems like sequence alignment, phylogenetic inference, drug design, etc. etc. So, a few major questions are addressed, which is you will find very similar to questions that are addressed in evolutionary concepts. So, the first being, how quickly do well adapted individuals emerge? So, after how many generations of a particular mutation, say for example, that's a good mutation that is helping a species survive, and after how many generations do these well adapted individuals emerge? Secondly, what genomic organization stratifies influence what genomic organization strategies influence adaptation? Number three, what characteristics of evolved organisms are outcomes of the evolutionary process? And finally, how do population structures and selection mechanisms impact diversity? We'll talk about all of these points while talking about genetic algorithms, but yeah, these are the types of questions that is generally asked from algorithms doing this kind of optimization. Okay, so one important part of evolutionary algorithms are genetic algorithms. So, in genetic algorithms, there are two essential components. One of them is the population, which can be a set of, you can imagine that as a set of uh, markers. Just give me 1 second. Hello. Hi, Kritika, I'm in a class right now. Oh, I'll talk a little bit. Okay. Yeah. So in genetic algorithms, we have majorly two components. One, population, which is you can assume as a series of differential equations if you want, and a fitness function, which is the cost function, which will actually optimize the algorithm. And these two features are only sufficient to create the skeleton of the genetic algorithm. And within this with all most genetic algorithms are modeled after Darwin's theory of evolution, asking similar questions that is asked during evolutionary processes, right? They use components of fitness, inheritance, natural variation, similar things that are involved in evolutionary processes, and through recombination and mutation. They model involving all these processes. They want to model how a genetic lineage will change and adapt over time. Therefore, all these components must be incorporated into genetic algorithms in order to be more accurately mimicking the natural selection. So this is what a population looks like. A population using the first generation, or F1, it is defined as to be the set of genes or chromosomes or other units of interest. So for example, you can assume this is a whole population. Each of these rows are one dimensional arrays. You can imagine, sorry, two dimensional arrays, you can imagine. No, sorry, these are one dimensional arrays only. Yeah, so these are one dimensional arrays, you can imagine. So 1 2 3 4 5 6 7 8 9 10 11 12. So 12 such arrays make this population. So each of this array can be viewed as a single model or a single equation, and a set of all these describing the whole process is known as the population. And each of unit of this population, so for example, this there are 12 units of this population. Each of them you can imagine as a chromosome. Inside each of them, you can imagine each of them as a gene, right? So this is the structure, general structure of a genetic algorithm. And there can be genes, chromosomes, or other units of interest depending on how granular you want it to be, right? And this generation can be represented in several ways, but the most common technique is to use bit arrays, where different permutations of zeros and ones represent different genes, right? So these are so this is the whole population. Then you have individual chromosomes. So individual chromosomes are represented by this binary form 0 and 1, and each unit of this individual chromosome is defined as a gene, which can be either 0 and 1. Okay. So this is how the genetic algorithm system operates. Yeah.
Hi,
Yeah, yeah.
so is it okay if I can?
Yeah, sure, you can speak.
Yeah, I just wanted to know. So, in context of the differential equations, suppose I have a system
Hmm.
wherein I have at least two differential equations, one for protein and one for maybe
Yeah.
the mRNA.
Yeah.
In the context of that, how does this bit vector fit into the differential equation or vice versa?
So this the bit vector I'm talking about, this is only using zeros and ones. So what you can
Yeah,
imagine is this: each of these chromosomes has one equation, and each of these
I see.
genes inside each of these genes, these are individual parameters of the equation.
Got it.
So that might not be zeros and ones. This is one such
Hmm.
representation. You can have full numbers and whatever you wanted in that. So it's like one equation. Inside one equations, the things that you are trying to find are the different parameters of the equation. So those will be individual
Okay.
genes. Together with the whole equation will be one chromosome, and like 25 of these equations will make one
The
population.
population.
Yeah,
Got it.
yeah.
Got it. Thank you.
Okay. So yeah, so this is how a genetic algorithm operates. So this is a iterative process. I'll go over each step. So you start here. You generate a random population of n chromosomes, which are suitable solutions for the problem. Then you do some sort of a fitness calculation. So you evaluate the fitness of fitness of each chromosome X in the population. So you have this set of, here I think it's 12 set of chromosomes in the population. So each of these chromosome will give you a fitness value depending on your optimization equation that you're using. So you'll need to have a fitness function or an optimization function that will evaluate the fitness of each of these chromosomes, right? uh, so then what you do is, after evaluating this fitness, you create a new population steps. So what it means in terms of a evolutionary concept is basically, you have a set of parents. Now produce a set of offsprings from these parents. Now in context of evolution, these offsprings will not be exactly same as the parents, right? So there will obviously there will be certain genes that will be exactly same, from the parents, but there will be, obviously, due to crossing over and other mutation events happening, there will be slight changes in the offsprings compared to the parents. So these are the types of elements that bring about this kind of variation or change in the offsprings, which first one is selection, second is crossover, third is mutation, and fourth is accepting. So this actually, these are the types of methods that are used to make the offsprings, which is the next generation from the parents, and you are creating a new population like that. So by selection, basically you select two parent chromosomes from the population according to their fitness. The better the fitness, the bigger chance to get selected. After selection, you do a crossover with the probability, with certain probability functions involved with the crossover, like which parameters can cross over and what is the probability of those. And basically, yeah, with a crossover probability, cross over the parents to form a new offspring. And if no crossover was performed, the offspring will be an exact copy of the parents, right? And you can introduce mutations in every generation. So with a probability function, maybe you can mutate certain of certain of the genes inside the chromosomes, and a new generation will will carry those mutations. If uh, like, we'll come to that, how we are evaluating this crossover and this new population that we are creating. We'll evaluate these again, but the idea is to create a new population through evolutionary concepts. It can be selection, it can be crossing over, it can be a mutation, or whatever. Now what you do is, once you have done this, and you get a set of offspring population. Now you do this same thing, you get this offspring population, and then you again do a fitness calculation of these offsprings. Then you do it for the next generation of it. Then you again get a new set of generation, you calculate fitness again, you do it. So this is an iterative loop, and you test it, and you do this iteratively until and unless you reach a termination point, which you will define. So basically, it can be the fitness function should reach this value to call to terminate, or you can set a limit on the number of loops this calculation must go on to terminate this. So there will be a terminating function depending on on the fitness values that you are getting from the new offsprings, and you can terminate once that condition is reached. So the idea is that once you reach that condition, that is your best possible solution, right? So you need to define your termination condition in such a way that it actually mimics what the perfect solution would look like. So this is how a genetic algorithm works. So this, it's an iterative process. You start with a population, then you calculate its fitness, then you do certain crossover, mutation, whatever, and you produce a new set of offsprings. Then you again calculate their fitness, do a similar sort of mixing and matching, and then you do again fitness calculation. So this goes on and on until you get to the termination point. So this is how a genetic algorithm looks like, and the most important part of this algorithm is to calculate the fitness, right? So the fitness function that you're defining will be is the single most important component of this algorithm, and depending on the fitness function, like how well you define it, the better solutions you'll get. So what is this fitness function? You can consider this fitness function as some sort of a cost function. You need to minimize this or you need to maximize this, right? So it will evaluate how well a design solution meets specified goals. In genetic programming and genetic algorithms, design solutions are represented as strings of numbers, which we discussed already, which are known as chromosomes, and the fitness function assigns a figure of merit to each solution based on a set of tests or simulation results. So, as I was saying, it's a function that will assign a particular value or some sort of a parameter to a particular set of solutions to denote how good that solution is actually. So, yeah, so this fitness function will determine which design solutions are retained and which are discarded, and this is essential for guiding the evolutionary process towards desired outcomes. So the thing is, the loops that you are running, ultimately your idea is to converge on something, right? Or converge on a particular value or a particular point where you have a set of these parameters as on a certain distribution. So for example, let us assume your termination point is that your all the parameters that you have assumed in basically the genes that you have assumed in each chromosome of your population, they must reach a normal distribution or something like this. I'm just giving it as an example. So until and unless it reaches that normal distribution point, the loop will go on and on. Now, if you design a fitness function that evaluates it and is not being able to converge all the solutions to a it does not have the property to converge all the solutions to a normal distribution, then this will not work. The loop will go on indefinitely and indefinitely. So designing of the fitness function, it becomes very crucial for the algorithm effectiveness, right? And a few challenges that are faced are basically uh, depending on how you design this particular fitness function, and you need to have very good idea, very good domain knowledge about the model that you are using, right? So there can be two types of these fitness functions. One can be a fixed, which can remain constant through all the loops. So basically one function that you define, and you are evaluating every generation of these solutions through that function only. But you can have a mutable function as well. So it can evolve. The function can evolve depending on how many generations you have reached and what generation you are exactly measuring the fitness of. So it can be a slightly dynamic function, or it can be a very fixed function depending on what you are hoping to get out of it. And so there's another concept called fitness landscape, which basically represents the fitness of each possible chromosome, and it helps visualizing the optimization process and identifying the optimal solution. So imagine a graph where basically in the first, you say for example, you need to minimize your fitness function. So in the first iteration, the first bar will be very high. Then in the next iteration, maybe it goes down a little bit. Then in the third, it goes down again. Fourth goes down again. Fifth goes down until and unless it reaches a certain value, which is the termination cutoff that you have achieved. You've given as a criteria. Now, the curve will look something like this. So it will start from the very top and it will come down, 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 down to reach the termination procedure. Now, that is what a fitness landscape means. So basically, you started with a very ineffective fitness, very like low fitness, then you move to a very high fitness. So this is what the fitness landscape defines. And so basically, the definition of the fitness function may require iteration, especially if your desired solutions are not achieved. Interactive genetic algorithms involve external evaluation by humans to address this challenge. So depending on the fitness function, so I'm talking about a very ideal type of fitness function, when in the first step it will be the highest, then next step it will go down again, go down till it reaches the termination criteria. But it can happen like this: it starts at high, next it goes down, next comes again high, then it goes down again, then it comes again high. So this iteration doesn't make sense, because you're not never going to reach that particular converging point, because it's like fluctuating. First step it's high, next step it's low, again it's high, again it's low, like this. It will not converge to something. So yeah, so depending on that, depending on the fitness function, your genetic algorithms like will take care of the optimization part. So defining the fitness function effectively is the biggest challenge of the whole algorithm, right? Okay, so I'll not go into very details because these are a little complicated if you look into the computation side. But the idea is very simple for biologists or like people who understand evolution to comprehend. So yeah, so leaving the encoding part aside, so it like as you were asking, like how does a like differential equation fit into a 0 1 kind of a system? It's not always 0 1. It's one of the form. It's binary encoding. You can have a, a, a whole set of encoding. For a differential equation, I'll probably go with a value encoding. So it's just I'll put the values of the parameters in as genes and constitute the whole chromosome. So yeah, so encoding is one part. And these are the things that are used, selection, crossover, and mutations are the things that are used to bring about randomness in every generation, to bring about a certain change from the parent generation to the next generation, right? So you can have a lot of um, variations in that as well. So these are the different types of techniques that are used. So for mutation, it's easy to understand. It's displacement mutation, inversion mutation, scramble mutation, etc. So generally how a mutation occurs, so you invert it, or you scramble it across, or you displace it. So it's basically a frame shift mutation, something like this. So, and in crossover you can have single point crossover, one point and you crossing over that. We'll come to the examples of this, so don't worry about that. But yeah, so you can have like two chromosomes, you can cross over at only one point, or you can cross over at multiple points, or you can do a uniform crossover or a shuffle crossover, depending on what suits your algorithm and the data best, right? So yeah, these are the different encoding schemes that we were talking about here. So these basically the purpose of this encoding is to convert the problem information into a suitable format, and these different encoding schemes are utilized based on the problem domain, each with its advantages and limitations. So as I was saying, depending on what you have, if you have differential equations, most probably you'll go for a value encoding. But if you have like a binary kind of a thing, in a logical or a boolean operator or a boolean model, then a string of zeros and ones, a binary encoding should work fine. Or you can have an octal encoding where you can represent anything between a 0 to 7 for all the parameters. Hexadecimal encoding, permutation encoding, so basically where the permutation is important. So what gene comes after what parameters comes after what, that if that is important, then a permutation encoding becomes a good technique to use. And the value encoding is simple. uh, so basically you just incorporate the values, no encoding whatsoever. And in tree encoding, the genes are represented in a tree structure of functions or commands. So basically there is a hierarchy. So this gene comes first, then these two genes come, then these three genes come from them. So there's a hierarchy in tree encoding. So depending on your problem, you might want to use this. And these are the pros and cons of each type of encoding scheme. So yeah, so mostly for our cases we use value encoding, and where there is no need for value conversion, which is a pro. But in the con, it requires specific crossover and mutation, because if you do a single point crossover, basically you are defining that at this position this crossover will take place. But in a real valued system, uh, that thing is basically not very effective. So if you want to do a single point crossover, it doesn't become much effective, because you're just changing the values of one gene to other. But in case of if you imagine a binary encoding getting crossed over, it's basically changing of the whole gene itself. Okay, so depending on your problem statement and the kind of solution that you're looking for, you can use different encoding schemes. Now, like we talked about, okay, yeah. So we'll talk about crossovers a little bit later. Let's talk about the selection first. So we are talking at this point. So you have uh, we talked about the fitness function. We'll talk about the crossover in the next few slides, and the different types of mutations that it can happen. And we're now talking about the selection procedure after the crossover or after the mutation has happened. How do you select for the best chromosome or the best solution, right? So selection determines which individuals participate in reproduction, and the convergence rate of the genetic algorithm is influenced by this selection pressure. So how do you select which chromosomes actually go in for the next round, and uh, which chromosomes don't, or which set of solutions go into the next round for the next offspring, and which set of solutions don't? So it can be completely random, like a roulette wheel. So basically it's just you spin and you get the best, and the point it stops, you use that as a selection criteria, right? So it basically maps individuals into a wheel based on fitness. There's a It's not completely random, right? So there's an element of fitness evolved associated with it, but some sort of randomness is also associated because it's a roulette wheel. And but it suffers from stochastic errors. So yeah, it's not the best mechanism, but it's a quite a simple mechanism. So you rank these chromosomes or the solutions based on their fitness, based on the fitness values of these individual solutions, and then you put them in a wheel, and the probability of getting one element out of the wheel is basically inverse of the basically no so the probability of getting any one element in the wheel is directly proportional to the probability of that being the best fit, uh, that being the best fit function for the next step. So basically, the rank that you give for each of these solutions for based on fitness. So basically, you rank these solutions based on fitness, and a solution that has a higher fitness value will have a greater probability of being picked from the roulette wheel compared to
Yeah.
yeah.
So for the rank selection, is it like if we consider it the fitness to be as a cost function? So the solutions that give the lowest cost function values will be highest ranked.
Sorry, I did not understand.
Essentially, in the fitness,
Yeah.
when we are doing this rank selection, so essentially it is loosely it can be translated to the minimizing the cost function, right?
Yeah, that is a criteria that you have put. It can be maximizing the cost
Yes.
function as well. So if you are
Ha,
thinking about
yeah.
minimizing the cost function, then it should be opposite. I am talking about a more
Ha.
generalized form ki, like say for
Okay.
example you are maximizing the cost function. So the maximum
Mm-hmm.
fitness value will be of a solution of and that solution will have the highest probability of getting picked. It's the inverse if you are like minimizing the solution, minimizing the
Mm-hmm.
fitness function. So
Yeah.
if you are
Yeah.
minimizing, the solution having the minimum value will be the most fit function, so that
Mm-hmm.
function will have the highest probability of getting picked. So it's just the like which is the most fittest of the solutions will have the highest probability of getting picked, and then comes the
Yeah.
second fit function will have the second highest probability of getting picked. It's like that. So it's just
Got
like
it.
it's opposite in case of minimizing and maximizing, but the idea is to
Mm-hmm.
pick the best fit solution. That is the idea.
Yes. Got,
Yeah.
got it. Thank you.
Okay. Yeah, so these are the other different kind of techniques. So uh, it one uses rank base, like this rank you define based on the domain knowledge, not on exactly on fitness values. But yeah, so you can use rank selection, you can use tournament selection. So basically in tournament you have selected individuals in pairs based on their fitness, and you uh, evaluate the fitness of all these small pairs of solutions, and you see which of the pair is operating best, so you take that out for the next round. So it can be in form of a single league form, like you rank them based on their fitness scores and you pick them out depending on the highest fitness, or you can have it like set of twos. Yeah, so two solutions, what is the combined fitness of that? Two solutions, what is the combined fitness of that? Like that. So these are different like techniques for using for basically selecting the solutions going in for the next round for offsprings. And one such technique is this stochastic universal sampling. Why I'm highlighting this, because this is actually a very, what to say, a very well known mechanism, because this actually is used for the traveling salesman problem, if you're aware of it. So the traveling salesman problem is basically you have a salesman in a city, and you have a set of delivery points, and you have to have the best route for the salesman. You have to find the best route for the salesman to go and deliver at all these points, but you cannot like ask the salesman to go through one road more than twice. So basically you can imagine that as a whole graph. So these are individual nodes are denoting the positions at which the salesman has to go, and there is one node at which the salesman starts. So basically what is the path the salesman should follow from one node to another, so that it can go to each node, but it does not have to traverse one path twice. So that is the idea of traveling salesman. So this stochastic universal sampling, basically it's an extended version of a roulette wheel selection, um, but it actually is very good optimized for a traveling salesman problem. So yeah, I just wanted to give an example out of this. And yeah, so there's this concept of elitism selection as well, so which ensures the best individual is always propagated to the next generation, and it mitigates the risk of losing the best solution during the selection. So basically when you are doing a roulette wheel or kind of a tournament selection, this can happen that the best solution is not getting selected for the next one, because there is a lot of probability involved there. So if you want to ensure that the best solution actually always goes on to the next generation, then it's the idea is to select, you categorize the solutions into different parts. So if certain solutions are the best solutions, you think you take them out already to go in for the next generation, and for the rest you do some sort of any of these techniques depending on the problem you are trying to solve, right? Okay. So yeah, so these are your pros and cons for each of these types. So yeah, so in elitism, the best individual is retained uh, in the population for the next generation. For roulette wheel, it's basically it's actually pretty. If you want to do something without bias, without knowing ki like which solution is actually the best given your current circumstances, and you just want to do it uh, based on pure luck and probability. So it does not include any bias. So roulette wheel is very good for that, but it has a risk of premature convergence, and it depends upon the variance present in the fitness function as well. So each of these techniques have their pros and cons. Depending on the problem statement you are trying to solve, uh, you need to choose your selection techniques, right? Now let's come to crossover. So what is crossover? So it's generally in biological terms, crossover occurs during meiosis, when basically two chromosomes, one two uh, two chromatids, sorry, not chromosomes, two chromatids, one from father, one and one from mother, they get crossed over. So one part of the mother chromosome cuts and binds to the father chromosome, and one part of the father chromosome cuts and binds to the mother chromosome. So that is what crossover is in biological terms. And in this case, it's kind of similar. You break the solution down into half, and you joined the first half of the solution to the second half of the next solution, and the second half of first half of the next solution to the second half of the first solution, something like this. So these crossover operators are used to generate the offspring by combining the genetic information of two or more parents. So for crossover you need minimum two solutions, right? So it's kind of this tournament thing if you want to do. So you take two together and you do crossover, and then you do uh, calculate the fitness, and you do it iteratively. So that is a good technique to do that. Yeah. So the well-known crossover operators are single point, 2 point, k point, uniform, partially matched, order, and etc. etc. There's a lot of it. So what are single point? Single point crossover is the break will happen at only one single point for both the solutions. So if you are the break is at the 50% point, so half of the solution, so half of the solution of the first will be attached to the half of the solution of the second. Similarly, half of the solution of the second will be attached to the half of the solution of the first. So that's a single point crossover. At one point you are breaking, and then you are attaching. It can be k point crossovers as well. So you can break at multiple points and crossover depending on how many crossovers you want, right? So there can be many variations of these that you can think of, and depending on if you want to increase the bias or you want to increase the randomness, you can go for n number of swappings or n number of crossovers. So that is depending on what exactly is you want as your outcome of these of the solution, right? So in a single cross point crossover, a random crossover point is selected. The genetic information of the two parents which is beyond that point will be swapped with each other. So basically these are your two solutions. So it's one is 0 1 2 3 4 2 9, and then there is 2 4 1 3 0 8 5 6 7 6 9. So at this is a single point crossover at which you are breaking at the fifth position, after the fifth position. So there are 10 solutions, so you are breaking up at the fifth position. So 0 to 5, so 0 to so 1 to 5 is the first set of so I'm not talking about these 0 1 2 3 4 5. I'm talking about the first, second, third, fourth, and fifth. The first 5 solutions are retained from the first one, along with second 5 solutions are just added to the first one, and this part is cut. So it's same. So this is the point of your crossover. You break it down here, then you attach the first part of the first solution to the second part of the second solution. So it becomes 0 2 0 1 2 3 4. Then this comes in 8 5 7 6 9, right? And it's the same for this one as well. 2 4 1 3 0, and then you have 5 6 7 8 9 here. So this is a single point crossover, right? You can have 2-point crossovers. Actually, you can have k-point crossovers at best, right? So in a 2-point and a k-point crossover, 2 or more random crossover points are selected, and the genetic information of the parents will be swapped as per the segments that have been created, right? So 0 1 2 is there, 3 4 5 6. So these two are your basically crossover points. One is after the third position, and one is after the seventh position, right? So basically you retain the first 3 positions of the first solution, and you swap out the middle section of the second second solution to your first solution, right? So it becomes 0 1 2, then this part goes in here, 3 0 8 5, and the last part is conserved again, 7 7 8 9, right? And you can this is one such possibility, right? So basically keep the end solution in parameters and just swap out the middle, or you can do it opposite as well. So you can keep the middle part and you can swap out the endpoints. There will be 2 crossovers there, right? So like depending the or again, so this requires, if you're applying this to a real problem, this requires the understanding of how that problem solution is going to turn out a little. If you do not have an understanding of that, if you're going in blank, then doing a single point crossover and a k point crossover is same for you, because you do not know how each of these affect the solution. So unless and until you know that this crossover will affect the solution in this manner, that then it's no point in doing so much of things, right? So it becomes important uh, to have the domain knowledge of how these solutions might converge. Okay. In uniform crossover, this is another type of crossover. The parents are not decomposed into segments, they are treated as each gene separately, right? So each of these solutions, each of these parameters are genes, so each of these boxes are one gene, and you randomly decide whether you need to swap the gene within the same location of another chromosome. So these are the 2 parent chromosomes. Now you randomly decide that these are the 3 positions that can change, that can be crossed over. So how will you, so I'll give you a small example. How will you decide that these are 3 random positions? Generally it won't be random. Generally you will decide on those parameters which you think are impacting the solutions the most. So this is your whole solution, but you think that the second parameter is actually impacting my solution the most. If I remove the second parameter, does my and swap it out with another one, does my solution still stand the fitness test? Is this, so for example, let us take this as your most fit solution from the previous step. Now you have another set of solutions, and this is one of them, the second one is one of them, but your first one is the most fittest, like depending on the calculation of the first step. Now you want to see ki, if I your hypothesis is that the second position, oh okay, I thought you said something, okay, Your hypothesis is that that's the second position's parameter. This parameter is actually contributing to the. Okay, sorry, I think there's some external noise. Okay, remove this. Okay, just give me a second. Yeah, sorry for that. Okay, so your hypothesis is, I'll go through this again. So you have you have say around 10 sets of solutions. Out of them, from the previous iteration, you know that this solution, the first one, is the best, right? Now you want to test if is it really the best, and what is the parameter that is contributing it to be the best, right? So you take the second best solution and you swap out these parameters. The one that you're hypothesizing is the contributing factor to this solution being the best solution, right? You swap that out. You swap the 4 with the 1, and you assume that these the other swapping points are also the parameters that are contributing it to be the best solution for this problem. Now you swap out all these, then you run this iteration again. Does this equation still stand the fitness test? Does this equation come out, or does this solution come out to be the top best fit solution of your problem again? If it does, then it means that those parameters that you swapped out are actually not that contributing to that solution being the best fit solution, right? So if in the second iteration it does not become the best fit solution, then you have your hypothesis will be confirmed that these parameters are contributing to your solution to be the best fit solution, right? So try to think it from that perspective ki, like, you are trying to solve a problem, but you do not know the exact solution of the problem. You have a set of solutions and you want to find out what is the best fit solution. Even if you have found out the best fit solution, you want to find out ki, like, is this actually the best fit solution, or if I swap out a few parameters here and there, will that become the best fit? So the thinking is like that. You need to think like that, right? So these are all crossover operators, right? So this is one type of mutation that you can incorporate here, right? So this is one type of mutation that you can incorporate here. Now you can just directly mutate the the um, the solutions itself, right? So depending on, again, this is very this is in relevance to the biological mutations that we see. So displacement mutation is basically displacing a substring within an individual solution. You can think about it as a frame shift variant. What happens in a frame shift variant? If you delete, say for example, there is a whole there's a gene, and inside the gene you delete two base pairs. So what will happen is the coding region will be shifted. The frame of the coding region will be shifted by two base pairs. So the protein that will be formed will be a malformed protein. It will not be the exact same type of protein that has been that was supposed to be formed, right? So it's similar to, like, it's like an frame insertion or an in frame deletion, something like that. So it displaces a substring within an individual solution, and it randomly selects a substring and displaces it to a new position. Variants include exchange mutations and insertion mutations as well. So you can either insert some extra parameters in the solution, or you can just exchange certain parameters inside the uh, inside the solution, so that the rest of the solution gets displaced a little bit. So that is what it means. So it's kind of a frame shift variant. Then you can have a simple inversion mutation. You would just randomly reverse the set of solutions. So if it is 0 1 2 3 4 5 6 7 8 9, it becomes 9 8 7 6 5 4 3 2 1 0, something like that. And it's basically an inversion mutation, the kind of mutations we also see in biological systems as well. The other type of mutation is scramble mutation, which basically randomly shuffles elements within a specified range of the individual solution, and then it checks if the resulting solution is improved or not. So these are different types of mutations. That there can be other types as well. You can just substitute one solution by another. That's a substitution. You can have like a deletion, but within frame. So what happens is you delete certain parameters out of the solution, but that actually doesn't change the the outcome of the solution, being the most fit or ranking wherever in the fitness category. So what it means is it's an in-frame insertion or an in-frame deletion. So even if you even if you delete those parameters, the it does not really bring such much of a difference in the final outcome of the solution, right? Yeah. So mutation is deliberate to stop falling of all solutions in a population into a local optimal of the solved problem. Offspring results from crossover randomly changes by mutation operation. In binary encoding, you can just switch from 0 to 1 and 1 to 0. Right? You can randomly select a few and you can switch them. So this is one example. So this is your original offspring 1, original offspring 2. In the mutated original offspring, you randomly take this position and you replace the 1 with the 0. And in this second case, you randomly take this position and you change it to 0, change it to 1, and you randomly take this position here, and this is not changed also at all. So basically, depending on the no, so first you need to hypothesize ki which parameters of your solution is the most important. As I was saying in the crossover part as well, if you have an hypothesis ki like these are the parameters in my solution that are most important, then you can mutate them, then you can do crossovers on them, just to establish the fact that these are actually very important, so that after mutation, after crossovers, after all these things also, all these things, the solution does not remain the best fit solution because you have mutated those parameters. So those parameters are actually the most important parameters of your solution. So this is the hypothesis that you need to have before mutating or before doing. Or you can do randomly to see if something converges, but there is no guarantee that it will do converge or not. You can, as I was saying, after every iteration you can find like the previous iteration at high fitness, next is low, then again it's high, then again it's low. It can go on and on. So you need to have a definitive understanding of actually how you are changing these parameters. Or if you do randomly, if you are in luck, you will get the lowest possible the highest fit function, or the lowest possible value of the cost function, even after randomly mutating. So yeah, depending on your use case, depending on what you want actually out of this algorithm, you can use whatever mutation operators or crossover operators you want. So we'll just combine all of these into one thing, which is one algorithm. So that's this Pigmo algorithm. So this stands for Python Parallel Global Multi-Objective Optimization. So this is a Python library. It uses a optimizer for basically you give a cost function and it will use techniques like this to optimize the problem and give you a perfect solution. So yeah, like do not focus on these unified interfaces, parallel processing, and whatever, but the idea is to handle multi-objective optimization problems together. These are problems where you're trying to optimize multiple objectives simultaneously, often with trade-offs between them, and this software actually provides the tools to find solutions that balance these competing objectives effectively. So like all these things that we talked about for genetic algorithms, if you make one such software where it actually can, if you can give it a set of solutions and a fitness function, it can optimize on its own. This is that software, which is the Pigmo. It's basically a library in Python which you can use to do this optimization, right? So it can work on various optimization problems, including constrained and unconstrained, single multiple objective, continuous integer, and even stochastic or deterministic problems as well. Okay, so yeah, this is the Pigmo optimization, the maths behind the Pigmo optimization software. It's basically uh, this is your objective. So you need to find x. You have a lower bound and an upper bound for x, and this is your cost function which you need to minimize, and these are your original equations that you want to solve, or these are extra constraints that you want to give. So yeah, so this, where x is defined as the cross between r and z. So r is basically the the fitness vectors, and z is your original set of equations. It's basically a cross product between these, if you imagine in mathematical terms. I'll not go into those details, but basically it is what is the decision vector or chromosome. So in this case, x is a set of variables of a chromosome which has different value. X can have different values for that for each of these genes. So you have one chromosome generated like this for x, you can have like 25 chromosomes like this for x, and now you can do that algorithm. You can run that algorithm and generate the best solution for that, as we discussed for genetic algorithms, right? So yeah, this pigmo and pagmo, this is basically the the idea behind this. Okay. So, do you have any questions in this part, or if not, we'll move to the problem solving part. So, if you have any questions, you can ask.
Like, we can move on.
Okay. 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 So the questions I'll put on screen for a minute or so, and after that, we'll discuss. Okay. You can either put the answers in the chat box, or you can just unmute yourself and let me know the answer as well. So,
I think the first two would be there, right? When the solver requires a guided approach.
okay, and when a suboptimal solution is sufficient. Yeah, that's correct.
Mm.
So,
So what do we mean by heuristics here? Essentially an out
heuristics is
of a
basically,
constraint, right?
yeah, yeah. You basically put a constraint on the thing that on basically, how do I define it? So, um, uh, so say for example, you're trying to solve a problem, and one way would be to go in blindly, do something iteratively and to find a problem, and the second would be to kind of have a guided approach to the problem, because you know that these are the kind of solutions that you can have. So you design your problem in such a way that you can get those solutions out of the problem. So that's a more of a heuristic approach, that you
Mm.
know something is going to happen, so you keep on doing that in order to get that particular solution. And in a blinded way, it will be just going iteratively over and over again with no
Mm. Mm.
confirmation of getting that solution, or no like guarantee of getting that solution. So
Yeah.
that would be the idea. And
So essentially, if I have a, for example, a time course data
yeah.
for essentially over a period of 1 hour or 2 hours to
Okay.
just check the growth of something. So we can have a upper bound knowing that whatever data we have, that this would be the upper bound growth for a given parameter.
Yeah, yeah,
Would it? Yeah, that would. Yeah,
that would
that is.
constitute this thing. Yeah, that's an
Yes, yes.
absolutely similar thing to do. Yeah. So
Mm.
basically, if you have a prior knowledge of the solution, and you want to design the algorithm so that you can get the solution out of that. So yeah, it's kind of a uh, supervised problem solving, something like that, if you want to. Okay.
Mm.
And again, so if you put in certain heuristics, if you put in certain constraints and everything, your solution will be suboptimal, because it will not be
Yeah.
an exact solution, because you have put
Yeah.
certain conditions on the solution and everything, and you're getting an approximate solution. So your solution will be suboptimal. So you only do this when basically your a suboptimal solution is sufficient for your problem. So yeah.
Mm.
Okay.
Mm. No, I think because in it would be dependent on the type of algorithm that we
Yeah,
use.
exactly. So yeah, depending on the type of algorithm that you use, if you want a very simple one, it will only choose the top fit function or a
Mm.
list of top fit functions from the top. But ideally, you should do some sort of crossover and then do some sort of, because the thing is, when you are picking up the solutions that goes on to the next generation, a certain
Mm.
amount of probability, if a certain amount of probability is involved in that, then you will
Mm.
not always pick up the first solution, which is the most fit
Huh.
solution. There will be some solutions that are not also fit that will be picked up. So yeah, that
Mm.
is the idea. So depending on the algorithm that you use, the fitness will be determined. Yeah.
I think the first three.
Just a second.
Yeah.
So okay, yeah, that's correct. Just to confirm, like, have you already solved these problems earlier, or like,
No, no,
no, no?
no,
Like,
no, no,
is it not the?
no,
It's not the exact same from the assignments, right?
no, no, no. These are
Okay, okay,
different.
okay. That's cool. I was getting
No.
surprised by that. Yeah. So yeah. So if it's a simple optimization problem with a few variables, there's no
Then there is
requirement
no point.
for an evolutionary algorithm, right? Yeah. Okay.
All, all of the above.
Yeah, it's true.
I feel like ABC.
Okay, so yeah,
Yeah.
it's a multi-dimensional direct
Mm.
search method, obviously, because you search across different solutions, and yeah, it's a multi-dimensional search. It follows the survival theory of the survival of the fittest, but the thing is, it comes with a little caveat, because when you are selecting for offsprings for the next generation, it's not exactly always survive. You're taking the fittest uh,
Mm.
offsprings into the next generation. Sometimes you are also selecting offsprings that are not fit as well. So it is survival of the fittest, but it's not actually exactly hardcore, like only the fittest will survive, the others will not survive. So it's
Mm.
not a binary thing, right? So it is survival of the fittest, but there are some caveats associated with it. It's obviously based on genetics and natural selection, because like,
Mm.
yeah, that's the whole idea of the genetic algorithm. So yeah.
Yeah. Recombination. I think the last two. Yeah.
Okay.
Because it is recombination.
Okay. Oh, I think I put the wrong answer here. Anyway, yeah, it is going to be the last two, I think.
Yeah, I mean
Yeah,
last two. Yeah.
yeah. So
So
basically,
crossover. Yeah.
in the second position, you swapped out.
Mm-hmm.
Yeah. So one second. A P
So
R T.
B is replaced with P, R is
Is it?
replaced with C,
Yeah.
E is there, and then S is replaced with the I think D.
Okay, just let me
I think
quickly check.
so.
So A is there. B is replaced with P.
Mm.
R. Basically,
And
C is
replaced with
replaced
C.
with R.
Mm.
E is there. D is replaced with S. Yeah, this
S.
is
Mm.
fine. Next one is B is there. No, A is there as well. A, C,
Mm.
D, and B. Oh, only E has been replaced with T here. Yeah,
Mm.
that's
Yeah.
fine. So the last two holds. The middle one
Mm.
is actually not a correct one. Just to be clear, because uh, it's basically you are increasing the parameters of the solution, or you're increasing
Mm.
the solution space. So that does not happen.
So that would be entirely a new dimension to the
That will be a
optimization tool.
completely new dimension.
Search
That
tree,
will
yeah,
like
search tree, search.
complete. This solution will represent a equation that is not exactly the same that you have started with. This will be a equation with twice the number of parameters that you are actually
Mm.
looking for.
Mm.
Yeah. So,
Yeah.
okay. this
It
was
is
also.
not a MATLAB package. And
Yeah.
yeah,
It is not a MATLAB. It is
it
a
is.
Python.
It is a Python. Yeah.
Yeah, yeah. I can't do anything about the questions. These are NPTEL questions only.
No,
But
that's it. So
yeah,
we can do all of them based on what parameters we give. So there are several
yeah.
different parameters for Big
True,
Mo,
true.
right? Topology, rings, and everything. So
Yeah, yeah. So
based on
Pigmo actually is the kind of the all-in-one thing that you
yeah,
have.
yeah, all
You
in
can
one.
do
Yeah.
everything, almost everything in that. So yeah,
Mm,
but the USP of Pigmo is that it can handle multi-objective functions, which is not very common in the rest of the softwares that are
mm,
available out there. So that
mm.
is an important USP for Pigmo. But yeah, you can
So
do
what
everything.
would multi-objective mean here? Yeah.
Multi-objective is meaning instead of one single cost function, you have five or six cost functions. You are trying to
Mm.
minimize all five or six at once, right?
Got it.
You either consider a sum of all six to be minimized, or you can do some sort of mathematical operator, other operators you can use, or you can just use individual functions and you want individuals to be minimized to the most. So some
Got it.
you instead the idea is instead of having a single cost function, you have multiple cost function.
Multiple. Got it.
Yeah.
Yeah. Single cross. Hmm. Story of the game. Too many numbers. I would go with actually the first three are there. Uh, no, I think. Hmm. I think first, second, and fourth. Fourth, first, second, and fourth, I guess.
Okay.
Yeah, I'm not done.
So I think fourth is not there. Third is there.
As a third.
Okay. So let's go one by one. So this is the fine. 0 1 0 1
Mm-hmm.
till here it's there. Then 0 is there. A 1 has been swapped out for this 0. So first is
Mm.
correct, right? Second is 0 1 0 1, it's there.
Mm.
This 0 has been swapped out by this 1, so 1.
Mm.
Okay. And the last, basically last two
Zero.
digits have
Yeah.
been swapped out here. So
Yes.
yeah, so this second is also fine. Third,
No,
I'm
I think
very,
the fourth one. Yeah, I
yeah,
think fourth
fourth
is
is
fourth. So.
basically second has been swapped out,
Mm.
and then 0 1 0 1, then this second last position has also been swapped out, right?
Mm.
So second position it becomes 1 1, okay, and second last position instead of a 1 you have a 0, huh? This is fine.
Yeah.
So third one,
The
fourth
first
one is
zero.
also fine. So
Mm.
I'm not going into the other options, but
Uh-huh.
yeah,
Yeah.
these are some,
Get the gist.
yeah. Okay.
Mhm. I think they did first five. I think maybe first three, four.
Okay.
Four, first four, I think. Particles on and would be random. It would be. No, I think first five. Yes, yes, first five. Yes.
I'm not sure. Okay.
Mhm. So
This.
admin search is a direct search method, right? Okay, but no, yeah, I mean it's not evolutionary. Yes, 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 got it. Take
Let
it.
me. I'm not sure about the particle swarm optimization. Let me search this.
Mm-hmm. I think particle swarm is a direct search method, but not a genetic evolutionary algorithm based direct search method.
But it's, I think, an iterative method only. Uh,
Hmm.
Let me go here. Hmm. Trying to improve a candidate with regard to a given measure of quality. Type of particle. Okay. Meaning it sounds like an GA, but let's see.
But not probably does not have these
Uh,
hybrid technique. Got
it's that combines the strength of both. Okay, okay. So that's not exactly genetic algorithm. Yeah,
it. Mm-hmm.
yeah. I'm also not familiar with this. Yep.
Okay.
You can see the question, right?
Yeah, I can see it. I don't see it. Acceptable mutations. We cannot have three together. Why not? In the first and the third can be done, not the second and the fourth one. Because, yes,
First and third, you said, right?
yes. Because we are so mutating the three with the two and four with the five.
Yep.
And we cannot have two genes
Yeah,
in each
you
of
cannot
them.
have, like, that is the thing. In a traveling salesman problem, you cannot travel the same
It's
distance.
not travel back, yes.
Yeah, so this and the last one does not
Mm,
make sense.
mm,
First and third. Yep.
mm. Like sure about the second, not sure about the third one. I don't know. Maybe second and third because
Yeah, I also think that one.
hybrid. It's hybrid, so I think it will maybe give a better
Yep, I
uh,
think, yeah.
solution of.
There could
Uh,
be solutions, but the genetic algorithm couldn't find them, and yeah, this is
mm,
the third option. Yeah, but there can be that there is no solution to your problem. I don't know why they
that
haven't.
would be a NP hard problem.
Yeah, but it can be
Hard, but
possible.
yeah, I mean,
Yeah,
yeah.
yeah. Yeah, I think, yeah, that's it from my side. If you
Mm.
have any questions or anything you want to discuss, because we have
So
time.
yeah, I just wanted to discuss the MATLAB in the assignment. There was this MATLAB problem wherein we have to check the parameters, right?
Okay,
Uh,
so one thing, I am not
if,
like familiar with the assignments that you're currently getting. So there's a
okay,
separate TA for that. Like you have a discussion forum, I think,
I see.
right?
Yeah. I guess I got it.
Yeah,
Yeah.
so
Okay.
I am not aware of the problems that you're getting
Mm-hmm.
for assignment. So assignment related questions, I won't be able to answer. If you want, if you want to know anything about the, like, any conceptual
Okay.
questions or anything like that, I can probably answer.
Mm-hmm. I think other than that is good. One thing that I had wanted to ask was just give me 2 minutes. I had written it down. So this yeah, so there is this idea of when we optimize the parameters, stiffness of the parameter, right?
Hmm.
Or stiffness. What does it signify? Essentially, from what I could understand was stiffness is essentially a measure of how robustly it could estimate the slopes or the differentials at each time point or
Yeah, it kind of is. Basically, the two concept. One is for robustness, one is for resilience, right? If
hmm,
if your solution is basically if your parameter is stiff and it's giving you a robust solution, so what it means is basically with the same parameter only it can describe a lot of states of the problem. So basically a single parameter with a single solution of that parameter, it can give
Hmm.
you different combinations of solutions which can describe the state completely. So by
Right.
stiffness meaning, from what I understand by stiffness is basically how well your parameter can explain your possible solutions given the variability
Hmm.
of the parameter.
Got it.
Okay. So if you don't mind me asking, what background are you from? And
So I am doing my PhD in computational biology in IIT
oh,
Gandhinagar.
oh,
Yeah.
okay. So your work,
Yes.
what are you working on?
So my work is on circadian biology. So one of
Circadian
my
rhythm. Okay.
yes. So I'm do a bit of protein dynamics, then gene regulatory network reconstructions,
Okay.
network theory, this and that, network pharmacology and stuff. So this is
Oh.
something that one of our batchmates is doing, but I thought it would be interesting to learn about all this.
Oh, okay, okay,
So
okay.
yeah,
So you're taking
yes.
this course for like just for knowledge, or like do you want to apply some of
Eh,
these?
So I'm thinking to apply it. So like given in the circadian biology, we have these time course expression data sets.
Okay,
If we can model, so it directly correlates to some disease pathologies, for example, heart rate
okay,
or some stroke. So there is an incidence that people have stroke at 4 a.m. in the morning,
okay. Acha.
and it
So
can
what
be
are you
mapped
exactly measuring across the courses? Is gene expression of some sort or?
as gene expression
Okay.
and protein expression. So essentially, gene plus the protein expression of the
Acha.
same gene for
Acha, acha.
as a different parameter. So if that can come, so we can understand how which pathway could be like
Okay.
getting disrupted at that point of time or something something of that sort.
Okay,
If you could
okay.
model the event, if you could predict it previously, if something is there a fluctuation in something at before night which you can predict. So that is something that I've thought of. It's not something that I'm doing right now, but that is one thing that people
Oh, oh, that's
can
great.
think
That's
of
great.
doing.
That's great.
Yes.
Okay.
So I meant to take it 2 years ago, but then right now I'm taking it. So yeah,
Yeah,
it's nice.
yeah, yeah.
No, I understand a lot of things now because my background was entirely different. It was in pharmacology and pharmacy, hardcore
Oh,
wet lab experiments.
okay, okay. Yeah,
And
okay.
then I switched to computational biology due to some reasons, and then
Okay.
right now I'm learning all this. So
So I primarily do not work in exactly systems biology. My work is mostly I
Mhm.
work with primarily genomics. So I handle
Ah,
genomics data and like mostly human genomics data and population genomics. So
okay.
I actually was working on systems biology a couple of years back. So
Mhm.
this course is offered by Professor Karthik Raman of IT Madras.
Yeah, yeah.
There's one professor in IISc called Professor Mohit Kumar Jolly. He also is one of the
Hmm.
like the
Yeah.
yeah.
I know John. Okay,
Yeah,
John.
so
Yeah.
I actually worked under him, and then there I learned systems biology and those kind of things, and
I see. Yes.
so I opted for TA for this course. So
Mm.
I am
Nice.
actually not, I do not directly work with systems biology stuff. I
I
only
see.
work, my work is with omics and related stuff.
Yeah. So I came went 2 years ago. I think I met Chirag and then
Chirag,
Devnath.
Chirag Jain.
Huh?
Chirag Jain is my guide, second guide.
I think he's your guide. Oh, nice.
Yeah,
So I
Professor
was there
Devnath
in.
Pal is
Uh,
also there. Yeah.
so I was there at the BD Bio
Ah,
2023.
yeah, yeah. He only organizes. Chirag only organizes. Yeah.
तो उसमें आया था. I was there. So we talk. So now, right now I'm not into to it going into genomics, but after this Genome India call, we are trying to think of genomics as well, but do something of some jivas or something. So yeah, that is
Oh,
that.
good, good, good.
Yeah,
Yeah.
yeah, it's necessary. So you are in your third year, right? Fourth year.
I'm in my second year. No, this is my second year.
Oh, okay. Okay. Nice. Yes, I think that was the only question that I had about the stiffness. I could try to read, but it was not very clear
Yeah.
what it meant
Okay.
about the stiffness of the parameter.
Okay. If you have
But
any like if you want any resources or anything, you can drop me a mail, or like if you want any help
sure,
regarding
sure,
your
sure.
understanding, I'll give
Uh-huh.
you my email ID. So you
Okay.
can drop me a mail. Oh, sorry, I wrote
Sure.
it wrong. Just a second.
Mhm. Got it. Nice. So that's nice. Got everything refreshed. So I was trying to attend the sessions but could not due to PhD fourth year
Yeah, yeah, I
stuff.
understand. I completely understand this.
So right,
But
yeah.
these
So
are
but
actually
but
are recorded if you want to like
yeah,
watch it back later.
I do refer to them all the time. So
Okay.
that is there. But yeah, I mean, live it is easier for me to understand and
Yeah, yeah,
discuss
yeah.
and
True,
do
true,
things like
true,
that.
true, true.
Because in the initial points, so because it is all everything is new to me.
Hmm.
Initially, it was difficult to understand the I would say the way assignments were coming out in the context of the material that was taught.
Okay. Okay.
So essentially, random networks and again the coding sections, they were something we just can watch and then but there was so essentially they were also supplemented with the test files which were used by Karthik or something.
Hmm. Hmm.
Then I would be better able to reproduce. I tried reproducing them, but it was because it was too fast to comprehend, so I did
Yeah,
not. But
yeah,
I
yeah.
think
So if you do not have a prior experience with MATLAB, it becomes a little difficult.
exactly.
Yeah.
Thanks to ChatGPT, like I know I now have experience in R, MATLAB, Python, Rust, Perl, everything.
Nice.
But
Great.
yeah, I mean it took some time. So, but rest other than that, everything's good. I think I'll be attending most of the next sessions. So yeah,
Yeah. Sure. Sure.
yeah,
Okay
sure.
then.
Okay, thank you so much.
Thank
Do
you.
I
Yeah.
call you Shama or Subra?
Uh, it's Shomo basically. It's a Bengali name.
Shomo.
Yeah.
Okay, Shomo.
Yeah.
Shomo. Okay, thank you so much, Shomo, for your
Yeah.
time. Yeah.
Thank you. Thank you. Bye
Okay,
bye.
bye bye.